Welcome back. In a previous video, we added an embedding layer to our Keras models. In this video, we talk about various options for embedding layers. What we're looking at is a recording of an embedding visualization using Tensorflow's projector. The dictionary meaning of the word embed is to fix an object firmly and deeply in a surrounding mass. So we see why this is a pretty good term to describe NLP embeddings. We take individual words and embed them in a new, highly dimensional but sparse vector space. There are a lot of embedding options, and I want to discuss some of the major ones so you're familiar with these terms. And I'll also take a historical overview of the evolution of embedding in NLP. First, keep in mind that embedding is a dimensionality reduction technique, and there are purely statistical approaches such as PCA, Principal Components Analysis, but I'm going to focus here on NLP approaches. The first embedding paper to make a splash in the NLP world was a 2003 paper from Benio and others. I have a link in the chapter. They proposed this idea of a learned distributional representation for words. And recall Ronan Colabert and the Sena parser we looked at earlier in the course. His 2008 paper was the first to point out the practical utility of embeddings. And if you look inside the Sena folder in an embeddings folder, you'll find the actual embeddings they learned training for several days over Wikipedia. The word-to-vec algorithm was developed by Thomas Michelot and others at Google. Here's his Google Scholar page showing all of the research that he's done in this area and others. The algorithm is based on the distributional hypothesis that similar words appear in the context of the same neighboring words. Training involves teaching the model to distinguish between co-occurring words and random words. There are two variations of this algorithm. On the left, we see the CBOW continuous bag of words approach, where a word WT is replaced by a random word. The task is then to learn to predict the correct word given its context. In the skipgram approach on the right, the distributed representation of the input word is used to predict the context. In either variation, the neural network is not created to build a classifier. The neural network exists merely to learn the weights, the embeddings. We can divide embedding algorithms into two camps: context-free embedding and contextual embeddings. An example of context-free embeddings is the glove algorithm from the NLP group at Stanford. Words were trained on a very large corpus of word co-occurrences. In a minute, we'll look at a notebook that used pre-trained glove embeddings instead of doing the usual embedding process during training. There are many other pre-trained embeddings available, including Facebook's FastText. And there's no simple answer to the question of whether you should use pre-trained embeddings versus adding an embedding layer. In general, and usually, the pre-trained embeddings will outperform the embedding layer approach, and the model should train faster. However, if your vocabulary is within a specialized domain, and you have a lot of training data, then it may work out best to add an embedding layer. In the GitHub, I have some notebooks that compare some results using an embedding layer in Keras versus using glove embeddings. This first notebook is not terribly interesting. I'm just importing some information, pre-processing it, randomizing it, splitting it into train and test, and then pickling everything so in the other notebooks I can just open them up. Alright, this notebook is going to use an embedding layer like we've seen before. I read in my pickled files, vectorize the data, set up my embedding layer. You have to specify an embedding dimension. I chose 128. We'll talk more about that later. And then I add the embedding layer in the model as we've done in previous notebooks. Train and test and get an accuracy of about 0.69. In this notebook, I'm reading in the same data, vectorizing, and then I have some code that will use the pre-trained word embeddings, which I download from here and expand it into a folder on my computer. This first block here is just going to create an index dictionary to map words to glove embeddings. Then we need to create an embedding matrix replacing the original token with the glove embedding, and that's what this code does. From there on, it's very similar to what we did in the other notebook. And if we look down at our results, we see it got 0.67, slightly lower. These results aren't terrible because it's a 20 class classification problem that's very difficult. And as always, I have to throw in the caveat that there are many parameters that we could have tuned and perhaps gotten different results. Another popular embedding is ELMo, Embeddings from Language Models, from Allen NLP. ELMo is a deep, contextualized word embedding model. The embeddings are extracted from the internal state of a bidirectional LSTM. This architecture helps the model learn contextual features of the data. One interesting feature of ELMo is that the representations are character-based instead of word-based, and this lets it learn morphological features. Allen NLP has demonstrated improved results on a variety of NLP tasks using ELMo. ELMo was trained on a 1 million word benchmark, plus Wikipedia and other text sources. Another option is Google's BERT, bidirectional encoder representations from transformers. That's an approach introduced in 2018. BERT pre-trains representations by embedding words in the left and right context as they are found in text. These pre-trained representations of words can then be fine-tuned in downstream NLP applications. BERT was the first bidirectional approach to pre-trained representations. BERT was trained by masking out 15% of the words in a huge amount of input text. And then a 12 to 240 layer transformer encoder was trained to predict the masked words. This training took 4 days on 4 to 16 cloud TPUs. The good news is that Google has released these pre-trained models so that you don't have to invest these resources. More good news is that these pre-trained models can be fine-tuned in about 1 hour of cloud TPU time or a few hours on a CPU. Before moving on, I want to circle back to a discussion of how to choose embedding dimensions if you're training your own embedding. There's a couple of rules of thumbs that I outline in the chapter, and one is that you should take the fourth root of the size of your vocabulary, and this is a rule of thumb for smaller data. 10,000 tokens is pretty small. If we take 10,000 to the fourth root, it's only 10. The second rule of thumb is that your embedding dimensions should be a power of 2. So in this case, we'd either move it down to 8 or move it up to 16. The reason for that rule of thumb is that memory in the size of a power of 2 will perform better with cache memory. However, if we have larger data like we have in this notebook, common choices are 128 or 256. The higher your embedding dimension, the longer it'll take to train the network, and it will need more data. If you don't have enough data, you'll probably overfit. On the plus side, higher dimensions can be more meaningful in terms of the relationships learned between words. One additional thing I want to discuss in this video is Tensorflow Hub. This is a repository of pre-trained models you can download and use in your code or experiment with online in Google Colab notebooks. There's a wide range of deep learning tasks available, including NLP tasks. The most popular embeddings are available, including BERT and ELMo, So you can add these embedding layers with just a few lines of code. Using an existing model with additional training targeting a different application is referred to as transfer learning in the literature. Let's look in the tutorials. Let's look at text classification. They're using the movie reviews. And when you build the model, you can actually download it, add it to your model, train and evaluate as we've done before. So this is a nice service in that you don't have to completely reinvent the wheel. You can take the wheel that someone else has already created and tweak it for your application. As an example of a language model built in an unsupervised approach from a huge amount of text, let's think about OpenAI's GPT-3. OpenAI is an AI company from San Francisco which has a nonprofit branch as well as a for-profit branch. GPT-3, that's Generative Pre-trained Transformer 3, is an autoregressive language model. In the embedding neural networks we discussed above, we trained only for the purpose of creating the embeddings. In contrast, in an autoregressive language model like GPT-3, it trains with a purpose, which is language generation. According to a paper released by the creators of GPT-3, the model learned 175 billion parameters and was shown to outperform prior models on many NLP generative applications such as machine translation. GPT-3 is a text prediction model, like our earlier experiments with Ngram models, but immensely more powerful. Given the massive nature of the project and some promising early results, a great deal of overhype was inevitable. The developers themselves acknowledge the limitations in this paper, where they say that GPT-3 can lose coherence over sufficiently long passages, can contradict itself, and occasionally contain non sequitur sentences and paragraphs. Facebook's chief AI scientist, Yann LeCun, noted that results in the question-answering domain were inconsistent. Even worse, the medtech firm Nabla studied using GPT-3 for healthcare with some disturbing results, which I outline in the chapter. Let's keep in mind the distinction between natural language and natural seeming language generated by a computer. When we humans speak, sometimes you do say what the expected response is, like, "How are you? I'm fine, thanks." However, meaningful conversation is not merely selecting the most probable response. There needs to be some underlying purpose that guides the speakers. Furthermore, humans understand a great deal about the context of conversations that AI systems can't match. Can we teach context and common sense to AI? Can we teach ethics to AI? These are open research areas.